Tonight, live at 5, the killer wave. One of the biggest earthquakes ever recorded sends a torrent across northeastern Japan, sweeping away everything in its path.
Earthquakes are making headlines again. From powerful tremors in Japan to sudden shaking in California and recent activity in Venezuela, it can feel like the ground is becoming more unpredictable. Is this just a series of unrelated events? Or are scientists seeing a larger pattern beneath our feet? New research is revealing surprising details about how Earth's massive tectonic plates interact and why some regions are facing growing seismic risks. So, what have experts just discovered? And should the world be paying closer attention? Join us in this video as we reveal the details. California's fault was quietly moving, and AI finally caught it. For years, scientists believed they had a good understanding of California's famous San Andreas Fault. It has been one of the most closely watched fault systems on Earth, with countless instruments tracking every shake and movement. But despite all that monitoring, something important was happening right beneath the surface without anyone noticing. It wasn't a major earthquake or a series of small tremors. Instead, the fault was quietly shifting in a way that traditional methods simply couldn't detect. A new study has now uncovered these hidden movements with the help of artificial intelligence, and the discovery is changing how scientists think about earthquakes. Led by Dr. Zara Zali of the GFC Helmholtz Center for Geosciences and published in Nature Communications, the research found dozens of previously unknown slow-slip events beneath the Parkfield section of the San Andreas Fault. Unlike normal earthquakes, these slow-slip events don't produce strong shaking that people can feel. Rather than releasing energy in a sudden burst, they slowly release built-up stress over several hours or even days. Because they happen so quietly, they leave behind only faint signals that are easy to miss. That is one reason they have remained hidden for so long. Scientists have known for years that faults don't move only during earthquakes. They can also creep or slip silently without causing noticeable ground shaking. The problem has always been figuring out when these quiet movements happen, where they occur, and whether they have any connection to future earthquakes. The signals are so weak that they often disappear within natural background noise, weather effects, and other slow changes happening inside the Earth's crust. To investigate this mystery, researchers focused on Parkfield, California. This stretch of the San Andreas Fault has earned a special place in earthquake research because it is one of the most heavily monitored fault zones in the world. For decades, scientists have filled the area with sensitive instruments, hoping to better understand how stress builds up and is eventually released along the fault. As Dr. Zali explained, faults can move in ways that don't generate strong seismic waves, allowing them to escape traditional earthquake detection systems. The research team wanted to know if years of continuous underground measurements contained hidden signs of fault movement that no one had recognized before. To find the answer, they turned to borehole strain meters. These instruments are buried deep underground and are sensitive enough to detect incredibly small changes in the Earth's crust. They continuously record tiny stretches and squeezes in the rock, creating an enormous amount of data over many years. That mountain of information created its own challenge. Small fault movements were buried beneath long-term ground shifts, seasonal environmental changes, and constant background noise. Sorting through all of it using traditional techniques would have been almost impossible. So the team used a different approach. Instead of looking for signals that scientists already knew, they developed a deep-learning artificial intelligence system capable of teaching itself to recognize hidden patterns directly from the data. Rather than following fixed rules, the AI learned what these quiet fault movements looked like, allowing it to spot events that had been overlooked for years. Dr. Zali said these events are extremely difficult to identify with conventional methods because they are small and hidden within complex background signals. Artificial intelligence made it possible to recognize patterns that otherwise would have remained invisible. The results surprised the researchers. Using the AI system, they created the first detailed catalog of short-duration slow-slip events ever identified at Parkfield using continuous strain meter records. The findings were also supported by nearby creep meters, providing additional confidence that these quiet movements were real. The study revealed that the slow slip events occurred at shallow depths and followed the same right lateral motion that defines the San Andreas Fault itself. But perhaps the most interesting discovery came when researchers compared the timing of these silent slips with low-frequency earthquakes, which are weak seismic signals often linked to underground fault movement. They found that activity from these low-frequency earthquakes tended to increase after the slow slip events occurred. That suggests the quiet movements may be changing stress levels along the fault, making later seismic activity more likely. Project supervisor Patricia Martinez Garzon explained that these slow fault movements are not isolated events. Instead, they appear to be connected to changes in earthquake activity, suggesting that slow slip could play a much bigger role in how stress builds up and moves along active faults than scientists once believed. In other words, some of the most important movements inside the Earth may not be the violent earthquakes we feel, but the silent ones we never knew were happening at all. But what does this hidden movement mean for future earthquakes? Keep watching to find out what this discovery really means for future earthquakes. At first glance, this discovery might sound like scientists have found a new warning sign for major earthquakes. But that isn't what the research says. The team did not conclude that these silent fault movements directly trigger powerful earthquakes. Instead, they found something more subtle but still very important. After many of the slow slip events, activity from low-frequency earthquakes increased. These are tiny seismic signals linked to movement deep within a fault. This pattern suggests that the silent slips may be changing the amount of stress along the fault, creating conditions that influence later seismic activity. That is an important distinction. The researchers are not saying a slow slip today means a large earthquake tomorrow. Rather, they believe these quiet movements may be one part of the much larger earthquake cycle. Understanding exactly how they fit into that process will require much more research. For years, scientists have mostly studied slow slip events in subduction zones, where one tectonic plate dives beneath another. Those regions have provided many examples of faults that quietly release stress without producing major shaking. But transform faults like California's San Andreas Fault have been much harder to study in the same way, especially when it comes to these short-lived slip events. That makes the new findings especially valuable. They suggest that slow slip may not be limited to one type of fault. Instead, it could be a common process that has simply gone unnoticed because the signals are so weak. The researchers also uncovered another interesting clue. They found that the relationship between the size of these slow slip events and how long they lasted closely matched patterns already seen in regular earthquakes. In other words, silent fault movements and destructive earthquakes may not be completely different processes. They could simply represent different points along the same spectrum of fault behavior. Imagine turning a dimmer switch instead of flipping a light on and off. Sometimes a fault releases stress so slowly that no one notices. Other times, that stress is released suddenly, producing the powerful shaking we recognize as an earthquake. This idea of a continuous range of fault movement is becoming increasingly important in earthquake science. The study also highlights another major breakthrough: the growing role of artificial intelligence in earth science. Instead of replacing scientists, AI is helping them uncover patterns buried within enormous amounts of data that would be nearly impossible to detect by hand. According to the research team, similar short-duration slow-slip events could be happening on active faults across the world right now. As more regions install dense monitoring networks and apply AI-powered analysis, scientists may discover that these quiet movements are far more common than anyone realized. Dr. Zara Zali says many important fault processes happen without producing damaging earthquakes. By finding these hidden signals, researchers can build a much clearer picture of how faults behave between major quakes and how stress slowly moves through the Earth's crust. Every new discovery brings scientists one step closer to understanding the complex forces that shape our restless planet. When another earthquake mystery reached far deeper than anyone expected, what happened next? Let's find out. Japan's Great Earthquake sent a shockwave to Earth's core, and it came back. While scientists were uncovering hidden fault movements beneath California, another remarkable discovery was helping explain one of the strangest mysteries ever recorded after a major earthquake. This time, the story began in Japan with the devastating magnitude 9.0 Tohoku Oki earthquake in 2011, one of the strongest earthquakes ever measured. The disaster unleashed enormous amounts of energy, triggering a deadly tsunami and permanently changing parts of Japan's coastline. But hidden within all the data collected that day was another mystery that scientists couldn't explain. About 15 minutes after the earthquake struck, Japan's highly advanced GPS network detected something unexpected. The entire country had shifted eastward by about 5 to 6 millimeters almost at the same time. The movement was so tiny that nobody could possibly feel it. Yet, Japan's network of more than 1,300 continuously operating GPS stations is so precise that it recorded the shift with remarkable accuracy. The strange part was that the signal didn't match the main earthquake, any known aftershock, or even a submarine landslide. For 15 years, researchers had no convincing explanation. Now, a study published in Science has finally solved the mystery. Led by Sun-Young Park of the University of Chicago, together with Hiru Kanamori of the California Institute of Technology and Luis Rivera of the University of Strasbourg, the research points to an extraordinary cause, a seismic wave that traveled nearly 2,900 kilometers to the edge of Earth's core before bouncing back to the surface. The wave responsible is known as an SCS wave, a special type of seismic shear wave created during very powerful earthquakes. Unlike the surface waves that produce the violent shaking people experience, SCS wave traveled deep inside the planet through Earth's solid mantle. Following the massive Tohoku Oki earthquake, one of these waves began an incredible journey. It traveled downward through the mantle until it reached the core mantle boundary, nearly 2,890 kilometers beneath the surface. This boundary separates Earth's rocky mantle from its liquid outer core, a region scientists consider one of the most extreme environments on the planet. Conditions there are almost unimaginable. Temperatures are believed to exceed 3,500 degrees Celsius, while pressures climb above 130 gigapascals. No human has ever reached this region, yet it plays a critical role in shaping Earth's magnetic field and internal dynamics. When the SCS wave reached the molten iron and nickel of the liquid outer core, it encountered a problem. Shear waves cannot travel through liquids. Instead of continuing deeper, the wave reflected off the core mantle boundary and began traveling all the way back toward Earth's surface, much like an echo bouncing off a canyon wall. Its complete round trip covered nearly 5,800 kilometers, making it one of the deepest seismic journeys ever connected to a measurable effect on Earth's surface. Researchers calculated that this journey would take about 13 minutes. That timing turned out to be the missing piece of the puzzle, because it matched almost perfectly with the mysterious GPS signal that had puzzled scientists for more than a decade. When the reflected wave returned beneath Japan, it still carried an unusual amount of energy. The Tohoku Oki earthquake had been so powerful that the SCS wave remained exceptionally strong even after traveling through nearly the entire planet. Instead of creating another major earthquake, the returning wave appears to have nudged faults that were already under tremendous stress from the main rupture. Scientists believe these stressed fault sections experienced countless tiny slips along tectonic plate boundaries almost simultaneously. Individually, each slip was incredibly small, but together they permanently shifted much of Japan eastward by around 5 to 6 millimeters. Even more surprising was the amount of energy involved. Researchers estimate that the combined fault slips released energy comparable to a magnitude 7.5 earthquake. Yet unlike a normal earthquake of that size, very little additional shaking was felt. The reason lies in how the energy was released. Instead of one large fault suddenly breaking apart, stress was gradually released across many smaller fault segments. The ground moved just enough to leave a permanent mark, but not enough to produce another destructive seismic event. Although seismologists have studied SCS waves for decades and regularly use them to investigate Earth's deep interior, no one had ever observed one returning with enough energy to permanently change the surface of an entire country. According to the researchers, the Tohoku Oki earthquake was an extraordinary event. The reflected SCS wave measured across Japan had a peak-to-peak amplitude greater than 1 centimeter, making it much stronger than similar waves produced by most earthquakes. Combined with faults that were already pushed close to failure, that extra energy appears to have been enough to trigger widespread but extremely gentle ground movement. Before reaching this conclusion, the research team carefully examined several other possibilities. Could the main earthquake have continued releasing energy? The scientists ruled that out because any continued rupture should have produced stronger movement closer to the epicenter, not an almost uniform shift across the entire country. Could an aftershock have caused it? Again, the evidence didn't fit. No recorded aftershock matched either the timing or the nationwide pattern detected by Japan's GPS network. What about a massive underwater landslide? That possibility also failed to explain why the movement appeared nearly simultaneously across such a large area. After comparing every available explanation, the researchers concluded that the returning SCS wave was the only mechanism capable of accounting for all the observations. The finding does more than solve a 15-year-old scientific mystery. It reveals that the effects of a giant earthquake may continue long after the strongest shaking ends, traveling deep into the planet before returning to quietly reshape the surface in ways no one had ever witnessed before. But the shockwave did not end there. It revealed something even bigger. Could Earth's biggest earthquakes have even greater reach than we thought? This discovery is changing more than just one explanation for a strange GPS signal. It is also changing how scientists think about the true reach of Earth's most powerful earthquakes. For decades, earthquake hazards have mainly been linked to three things: the main rupture, the aftershocks that follow, and, in some cases, destructive tsunamis. Those have long been considered the primary dangers after a major quake. But this new research suggests the story may not end there. According to the study, powerful seismic waves can travel thousands of kilometers through Earth's interior, reach the boundary above the liquid outer core, reflect back toward the surface, and still carry enough energy to influence faults that are already under stress. That doesn't mean every major earthquake will trigger this kind of response. The Tohoku Oki earthquake was exceptionally powerful, and scientists believe that extraordinary strength allowed the returning wave to survive its incredible journey through the planet. Even so, the discovery raises an important question. Has this happened before without anyone realizing it? Researchers now want to find out. The team plans to revisit data from several of the largest earthquakes ever recorded, searching for the same hidden pattern. These include the massive 2004 Sumatra Andaman earthquake, which triggered one of history's deadliest tsunamis, the record-breaking 1960 Valdivia earthquake in Chile, the strongest earthquake ever measured, the devastating 1964 Alaska earthquake, and the powerful 2010 Mole earthquake in Chile. With today's advanced computer analysis and far more detailed seismic records, scientists hope to determine whether reflected SCS waves quietly influence the ground after those events as well. If they find similar evidence, it could reveal that this process is not unique to Japan, but part of how the planet behaves during its most extreme earthquakes. The study also reminds us of something remarkable about modern Earth science. Much of what we know about our planet comes from places no human has ever reached. The deepest hole ever drilled into Earth is Russia's famous Kola super-deep borehole. Even after years of drilling, it reached only about 12 kilometers beneath the surface. That may sound impressive, but it barely scratches the planet's outer layer. Below that lies Earth's vast mantle, stretching nearly 2,890 kilometers before reaching the liquid outer core. Those immense depths remain completely beyond our physical reach. Since no one can travel there or collect rock samples directly, scientists depend on earthquakes themselves to explore the planet's hidden interior. Every powerful earthquake sends seismic waves racing through Earth, carrying valuable information about the materials they pass through. By measuring how those waves travel, slow down, bend, or reflect, researchers can build surprisingly detailed pictures of regions they can never visit. The Tohoku Oki earthquake has now provided one of the most extraordinary examples of this natural process. A seismic wave traveled all the way to the edge of Earth's core, bounced back toward the surface, and left behind a tiny but permanent mark that instruments detected across an entire country. That single observation offers a rare glimpse into the deep connection between Earth's hidden interior and the crust where we live. It also serves as a reminder that our planet is far more interconnected than it appears. Events taking place thousands of kilometers beneath our feet can sometimes leave subtle fingerprints on the surface, revealing that the forces shaping Earth continue to surprise even the scientists who study them every day. So, if earthquakes are reaching farther than expected, are they also happening more often? Stay tuned to find out. Are earthquakes happening more often? The truth behind the global activity. When people hear about major earthquakes happening in different parts of the world within days of each other, it is natural to start looking for a pattern. Venezuela experiences a devastating earthquake sequence. Japan records powerful seismic activity. The Philippines is hit by a magnitude 6.5 earthquake. Papua New Guinea experiences its own series of tremors. Nicaragua reports a magnitude 5.2 earthquake. Seeing all of these events appear in headlines at the same time can make it feel like something unusual is happening. Many people begin asking the same question: is the planet becoming more active? Are earthquakes increasing? The honest scientific answer is no. Earth itself is not suddenly producing more earthquakes than normal. But the reality is more complicated than simply saying nothing has changed. Every single day, thousands of earthquakes happen around the planet. Most of them are so small that humans never feel them. They are only detected by sensitive instruments placed around the world. The earthquakes strong enough for people to notice are still happening constantly, with hundreds occurring globally every day. Earthquakes measuring magnitude 6 or greater happen roughly 120 to 140 times each year on average, meaning that somewhere on Earth, a significant earthquake occurs about once every few days. So when several major earthquakes appear during the same week, it may look unusual from a human perspective, but statistically, it is something scientists expect to happen. The reason is simple. Earth is always moving. The planet's outer shell is broken into massive pieces called tectonic plates. These plates are constantly shifting, colliding, separating, and sliding against each other. The energy created by these movements is eventually released through earthquakes. However, not all earthquake zones are connected. The earthquakes in Venezuela and Japan, despite happening around the same period, were caused by completely different geological systems. Venezuela sits along the boundary between the South American plate and the Caribbean plate. This region is dominated by a transform fault system, where sections of Earth's crust slide horizontally past one another. Japan, on the other hand, sits along one of the most complicated tectonic regions on Earth. It is located near a subduction zone where the Pacific plate is forced beneath other plates, including the Okhotsk microplate and surrounding tectonic structures. These two earthquake systems are separated by thousands of kilometers and do not influence each other in any meaningful seismic way. The earthquake in Venezuela did not trigger the earthquake in Japan. The two events simply happened within the same period of Earth's natural activity. What these recent earthquakes truly highlight is something much broader: the incredible activity of the Pacific Ring of Fire. Stretching around the Pacific Ocean like a giant horseshoe, the Ring of Fire covers roughly 40,000 kilometers of active tectonic boundaries. It includes some of the most earthquake-prone regions on Earth, including Japan, the Philippines, Papua New Guinea, California, Mexico, Chile, and New Zealand. This region alone produces around 90% of the world's earthquakes and is home to approximately 75% of the planet's active volcanoes. The Ring of Fire is not becoming more dangerous. It has always been active. Every week, seismic instruments detect movement throughout this zone because these faults are constantly adjusting beneath the surface. What has changed is not the Earth. What has changed is us. Over the last 70 years, the world's population has grown dramatically, and millions of people have moved into massive cities built directly on or near active fault zones. This is where the real danger lies. Cities such as Tokyo, Jakarta, Manila, Karachi, Los Angeles, Istanbul, Mexico City, Lima, and Bogota are all located in areas where powerful earthquakes are possible. The question scientists and disaster experts focus on is no longer whether these places will experience major earthquakes. Eventually, they will. The bigger question is, will the buildings, roads, hospitals, and emergency systems be ready when that day comes? That difference can determine whether an earthquake becomes a manageable disaster or a devastating tragedy. Venezuela's recent earthquake showed how much damage can be amplified by conditions that existed long before the ground started shaking. Years of economic struggles meant many buildings received little maintenance. Poverty forced millions of people to live in structures that were never designed to survive major earthquakes. Emergency systems lacked the resources and preparation needed for a disaster of this size. The earthquake itself was powerful, but the vulnerability surrounding it made the consequences far worse. Japan represents a very different approach. For generations, Japan has invested heavily in earthquake preparation. Strong building standards, advanced warning systems, public education, emergency drills, and disaster planning have become part of everyday life. Japan's resilience was not created overnight. It required decades of investment, planning, and commitment. But the results are clear. A major earthquake that could overwhelm another country can become a far more manageable emergency when a society is prepared. California falls somewhere between these two examples. The state has made major progress in earthquake safety. Systems like Shake Alert can provide seconds to tens of seconds of warning before strong shaking arrives. Modern buildings are designed under strict earthquake codes, reducing the risk of collapse. However, challenges remain. Many older buildings still need upgrades. Retrofitting vulnerable structures has been slower than scientists would like, especially in communities with fewer financial resources, and there is still a gap between what researchers understand about earthquake risks and what many people do to prepare for them. The important lesson is that preparation matters. People cannot stop earthquakes from happening, but they can reduce the damage they cause. Simple steps can make a major difference. Having at least 72 hours of emergency supplies, including water, food, medication, first aid materials, and flashlights, can help during the first critical days after a disaster. Knowing how to shut off gas lines, securing heavy furniture to walls, and creating a family communication plan can prevent injuries and confusion when normal systems fail. Understanding evacuation routes and knowing where to go after an earthquake can also save valuable time. These actions do not require years of planning. Many can be completed in a single afternoon. The Earth will continue moving. Faults will continue shifting. Earthquakes will continue happening. The real difference comes from how prepared people and communities are when those movements finally reach the surface. Because the biggest earthquake risk is not only the power of the planet beneath our feet, it is whether we are ready for it when it arrives. If earthquakes cannot be stopped, what can humanity do to survive them? Keep watching to find out. The Earth will keep moving, but our response is our choice. The planet has been moving for billions of years. For 4.5 billion years, tectonic plates have shifted, faults have slipped, and enormous amounts of energy have been released beneath the surface. Earthquakes were happening long before humans existed, and they will continue long after we are gone. There is no technology that can stop earthquakes. There is no reliable method that can tell us the exact day, hour, and location where the next major earthquake will strike. But there is something we can control: how prepared we are when it happens. An earthquake itself is a natural event, but the number of lives lost is often determined by human choices made years or even decades before the ground begins to shake. Venezuela showed the devastating consequences of what happens when a powerful earthquake strikes a vulnerable society. A magnitude 7.5 earthquake became far more destructive because it collided with weakened infrastructure, economic hardship, and limited emergency resources. Japan showed a different possibility. By accepting the reality of living in one of the world's most active seismic zones, the country invested for generations in stronger buildings, emergency planning, public awareness, and advanced technology. The earthquake risk did not disappear, but the impact was reduced because preparation became a priority. Now, California remains one of the biggest questions. Scientists have long warned that major faults across Southern California are capable of producing powerful earthquakes. Recent research suggests some fault systems have been building stress for centuries, increasing concern about future seismic activity. The so-called Big One is not just a movie idea or a distant possibility. It is a real geological threat that experts have studied for decades. But what happens when that earthquake eventually arrives will depend on decisions being made today. It will depend on how cities prepare, how engineers strengthen buildings, how governments invest in emergency systems, and how individuals prepare their homes and families. Earthquakes are unavoidable. Destruction is not. The planet will continue moving exactly as it has for billions of years. The question is whether we will continue ignoring that reality or whether we will learn to live with it. We will continue following the latest developments, from aftershock activity in Venezuela to new research on the San Andreas Fault and seismic updates from Japan. Because understanding earthquakes is not about predicting the impossible. It is about preparing for what we already know is coming. So, what do you think about what scientists revealed? Let us know in the comments section below. In the end, earthquakes remind us that Earth is always changing. While we cannot stop nature, we can prepare, learn, and protect each other. If you enjoyed this journey into Earth's mysteries, like, subscribe, and stay tuned for more discoveries.